read the chapters like solid as well as fluid. Okay, so let us begin. Okay, so let us start with the same word, bulk properties of matter, right? So what is a bulk property? Bulk property is that intensive property of a object, okay, which doesn't depend upon the size of the system or amount of the material. Okay, it always not depend on the size of the system as well as amount of the material, means how much molecules are there, how much particles are there, it doesn't depends on, right? And what are those properties? Those properties are like elasticity, stress, strain, okay, all these things. Okay, so first one that we are going to read is the elasticity. Okay, so before going to the concept of elasticity, first we have to see what is exactly your interatomic forces or intermolecular forces. Okay, so let us take one non-rigid particle, molecules or atoms. Okay, suppose I have taken two atoms, or you can say this is a non-rigid body, okay, a flexible kind of body. In those molecules, in between them, let us attach a spring. Okay, for an example, okay, let's see, just imagine if I will compress this one, this is the distance. Okay, so let me take it as r. So if I will compress this one, these two molecules always try to expand. Okay, according to the law of nature, what is that? The molecules or any object always tries to come back to its original position. Okay, it always tries to come back to its original position. So what they will do? They will come back to the same position by expanding themselves. If I will expand this one, these two molecules, then they will always try to come back to the main position by compressing themselves. If we will expand, they will compress. If we will compress, then they will expand. This kind of thing that is happening, if we will expand something, then they will come back to the original shape. This is known as the property of elasticity. This is a property of matter due to which it can develop a force within itself to oppose any deforming force. Deforming force is that force, if you will apply that one, you can change the shape of a material, you can change the configuration of a material, you can change anything in that material. Okay, that is known as the deforming force. So this property, the elasticity property, is what? This property of matter due to which it can develop a force within itself to oppose any deforming force. That is obviously what? A restoring force. Like for an example, let me take this wire. Okay, inflexible object, it comes back, right? Inflexible object means you can say a rubber, or you can say a elastic rubber, or you can say what you can say, some various particles like sponge is also there. If you will compress, then it will come back to the original position. Okay, but in some material like steel or something else, okay, obviously the elasticity property is working. Okay, that doesn't mean that if elasticity is there, it has to come back to its original position. No. Okay, some materials are there, they apply the force, they apply the restoring force, but they cannot come back to the original position because of their nature. Suppose I will take this steel wire of length L, okay, and I will expand, okay, by applying a weight mg. Okay, now what happened? Thus this wire is expanded up to a length delta L. Okay, up to this much length it has expanded. Okay, this is the point delta L. Okay, how much length it has expanded? Suppose delta L. And how much weight I have applied? Mg. Okay, now where you are applying the deforming force? You are applying the deforming force in the downward direction. And where the restoring force is being developed? The restoring force is being developed in the upper direction between the molecules. Okay, let us see in detail. When we will apply the deforming force, what is going to happen? This is one molecule and this is one molecule. For an example, if you will expand, this molecule will come back to this position. So what will happen? Automatically there will be a force of attraction will be there between these two. Why? Because they don't want to separate and they always tries to come back to their original position. They will not come back. That's a different story. But what is the property of elasticity says us in physics? The physics has a clear definition that if it has an intention to come back to its original position, then you can say it is a elastic body. The elastic body doesn't mean that only a rubber, or you can say that you are raising as a hairband or something else. No. If any material is creating within itself a restoring force, then you can say that is a elastic body. Right? So the clear definition is what? The clear definition is this is the property of matter due to which it can develop a force within itself to oppose any deforming force. Right? Now what will going to happen after some time? Suppose you have applied the weight, and when this deforming force, okay, is equal to this restoring force, now what will happen? This will stop here. It will expand up to this point, and up to the at this point it will stop. Why? Because your deforming force now is equal to the restoring force. If you will apply more weight on that, again, as the deforming force is higher than that of your restoring force, again it is going to expand. But what is the intention of the molecules present here? The intention of these molecules present here always tries to come back to its original position. And that is why, because of the interatomic forces, or you can say intermolecular forces. There is no such material that is not having these kind of properties. So it always have a interatomic forces. Somewhere it is high, like rubber, somewhere it is less. It can come back in some material, it cannot come back to the original position in some material. Okay, now a very famous question that is going to be asked in this chapter, that is, who is more elastic in nature? Okay, the property of elasticity is more in steel or rubber. The question is, the property of elasticity is more in steel or rubber? Most of you will think that the answer is rubber. No. Because to expand a rubber, suppose I will take one rubber here, to expand a rubber up to a 1 mm distance, up to this 1 mm distance, we require a less amount of force. Why we require a less amount of force? Because the interatomic forces between the two atoms is very, very less. That is, the restoring force is very, very small. So if you will apply a very small force also, very small deforming force also, it is going to expand up to 1 mm. Now think same about a steel wire or a steel material, anything of the same mass. You tries to expand it up to 1 mm, and you know it very well, to expand it up to 1 mm, how much force you require. Obviously, if you are going to expand it, then you obviously require a maximum force, maximum deforming force. Right? Why? Because here the interatomic forces are very, very strong in case of a steel wire. Why? Because they doesn't want to separate themselves. The amount of restoring force working here is very, very high. So what you need? You have to apply a larger weight here, like in this rod. In this rod, you have to apply a mg that is very, very high. Then only you are going to expand this particular rod or wire. Okay, so who is more elastic in your physics? The simple answer is steel, because the intention to come back to the original position is very much high, or the interatomic forces between the two atoms or between the two molecule is very, very high in case of a steel. So that's why you can see and you can say that a steel is more elastic than that of rubber. Never forget. Okay, so this force where the steel always wants to come back to the original position is known as the restoring force. Okay, now next point, stress. Next property is your stress. Okay, all of you understood up to this? Yes or no? Say me yes if you understood.
Yes, sir.
Yes, sir.
Yes, sir.
Action and reaction. See, the point where you are applying the force, then and there only the reaction is going to appear. That means, suppose for an example, here two atoms are there. Here if you want to expand to this one up to this side, so obviously there will be a reaction is going to develop in the opposite direction. Okay, so this reaction force is right now what? The restoring force. So between the two molecule a reaction force is going to be developed, and it will start when you are going to apply a force, that is a deforming force. Okay, so moving on to the next one, that is stress. Okay, so what is stress? If we are going in detail what is stress is all about, then stress is totally depending on the restoring force. Okay, stress is a measurement of how much restoration force is being developed. Okay, stress means what? If you will expand something, this wire is obviously going to get a pressure on it, right? And that pressure is nothing but what? A stress, right? And why it is generated? Because you have applied a deforming force due to this mg in this direction, right? So because of that a stress is being produced here, and that stress is because of what? The restoring force. That stress is because of the restoring force. And how we can calculate this one, this restoring force? We can calculate this restoring force by applying a very suitable method. What is that? Suppose this whole wire, okay, whole wire of area A, area of cross section A is going to experience a restoring force F. Okay, then one unit area, okay, one unit small cross section area, okay, how much force it is going to experience? Obviously F upon A. Okay, so this is the formula of your stress, force upon area. This is the formula, same as that of your pressure. Okay, so we have to focus on the area if we want to compare two different materials. Okay, in one unit area how much force is going to be applied. For an example, if I will take two wires, one is of steel and one is of iron, okay, both are of the same mass, both are of the same length, and if I want to calculate what is the stress produced if I will apply the same mass on it, same force, same deforming force on it, then what I have to check? How much restoration force is being produced in this area, in this unit area. First I have to calculate the unit area, then automatically I will get the full area calculation, right? So if whole area, okay, if the whole area is going to get a force of F, then one unit area is obviously going to get F upon A. This F upon A is known as stress. Okay, again, if one bigger area is going to get a stress by applying a force F, then the unit area within that particular object is going to get a stress of F upon A. right? So this is the formula of this one stress, and we can say it has of two types. One is what? Normal stress. Another one is your tangential stress. Okay, let us see in detail. And the notes you can see elasticity, that the same thing that I have told is being written here. The next stress. Okay, and stress, what is being written? See clearly. We have to focus on area if we want to compare expansion of two materials, okay, or two different wires. Okay, two different wires. So area A of the wire 1 experiences force F. So one unit area is going to experience a force of F upon A. So what is the stress? Similarly, it is going to be compared for the second wire. Then we will calculate that who is getting more stress, the wire 1 or wire 2. Okay, so that is the calculation method for a stress. So what is a stress? So stress is nothing but force upon unit area. Okay, now what is normal stress? Normal stress is what? If this is the area, okay, and if the force is being applied 90 degree or normally to that of your surface, okay, then you can say this is a normal stress. The stress generated if the deforming force applied is 90 degree to that of the surface, then you can say it is a normal stress. Then suppose in that same body only, what I will do, I will create a structure like this. Okay, and that after that I will apply a force by applying a rod like this. Okay, I will apply a rod like this, and I will apply a force in this direction. So what you can say, you are applying a force which is making 0 degree with that of the surface or with the area of the system, right? If this angle is making 0 degree, then obviously it's a tangent, so it is known as the tangential stress. Okay, now the next point is your strain. Okay, the stress is over. Next one is the strain. Strain calculation is what? Strain is nothing but the ratio. It is just a ratio. Means we need to find out how much we have deformed, or you can say how much change has taken place in a particular object. Then we can say it's a calculation of strain. So the simple formula of the strain is change in configuration, okay, change in configuration to that of the original configuration. How much it has changed and what was the condition before. Okay, suppose in a wire, okay, previously it was like this is the original configuration, and because of applying a deforming force it has expanded up to this. Okay, it has expanded up to this. So what is the change in configuration? This is the change in configuration. Okay, or you can say this part. Okay, this part is only the change. You can represent is a delta L. So delta L upon the original length. Original length is L, so delta L upon L is going to give you the strain result, right? You can see in this figure, and that calculation is known as the longitudinal strain. Okay, what is a longitudinal strain? If we are having a rod like this, steel rod of length L, by applying a weight mg, it has increased up to a length delta L. Then what should be the strain? The strain is change in configuration. So what is the change in configuration? Delta L. And what was the original configuration? This is the original configuration. And what was the length? L. So this will give you the strain ratio. So basically it is what? It is the ratio of change in configuration to that of the original configuration. Okay, so now next one is, this is longitudinal strain. Next one is volumetric strain. Okay, as you can see here, suppose I have taken a balloon like this, which is having a volume, this one. Okay, and let us see, the water is there inside it. Okay, and previously, or you can say original volume is this one. Okay, and after I will expand it, it will create a volume like this. And what is that? Previously the volume is V, and now it is changed, and let us take the name of the change, or let us represent it with delta V. Okay, let us represent with delta V. So what is the change here? V plus of delta V, because previously it was V and now it has changed to delta V. So what was the change in volume? V plus of delta V, right? So now if we want to calculate what is the volumetric strain, the volumetric strain is the change in configuration. The change in configuration was what? Delta V, okay, upon the original configuration. What was the original configuration? Only the V, right? So this kind of thing is known as the volumetric strain. Okay, if we want to consider about the volume, okay, change in volume, that is delta V, and original volume is your V. Which was the original volume? This is the original volume. Okay, now next is your shearing strain. Okay, next is your shearing strain. How can we will calculate this shearing strain? If we are going to apply a shearing stress, then obviously a shearing strain is going to be produced. Okay, how we can do that one? Same box is there, or steel box is there on an example. In that, one iron like structure is there present like this. Okay, now I will apply a rod here, okay, and I will pull in this direction. Okay, so where I am applying the force? Ultimately I am applying the force in this direction. And how much it making angle? It is making angle 0 degree with that of this area, with that of this area, right? So now the structure is now bent like this. The structure is now bent like this. So how much it is being changed? If somebody will ask you how much it has changed, it has changed up to an angle theta. How can you calculate this one? By observing the angle theta. Previously the angle was like this, and now because of this one, this angle is now changed. And how much is this angle? Theta. And this theta is going to give us what is the shearing strain result. So theta, you know it very well. What is the formula for theta? Arc upon radius. Okay, so previously the arc, or you can say the, what you can say, box, this one is delta x. Okay, and after expanding this one in this direction, there was a length change in length is being produced, that is delta x here. Okay, so previously it was x like this to this. Okay, and due to applying the force, it has expanded up to delta x. So if you will see this as a triangle, okay, this one as a triangle, and this angle is theta. So what is the formula for theta? Theta equal to arc upon radius. Okay, so here is the arc. What is that? Delta x. Okay, and what is the length here? This one. Okay, so delta x upon L. Right, so this is known as what? Shearing strain. Okay, understood up to this? Yes or no, all of you?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Now next, the Hooke's law. Okay, what is a Hooke's law? Okay, Hooke's law is that in a perfect elastic body, Hooke was a scientist and he has given one law. What is that? In a perfectly elastic body, the strain produced is directly proportional to the stress. Okay, in a perfectly elastic body, okay, if it is a perfectly elastic body, right, then whatever you will apply the stress, okay, whatever you will apply the stress, that much of strain it is going to appear here in that particular object. Okay, for an example, if it is perfectly elastic wire, I will take it as steel wire, suppose this one. Okay, and it is perfectly elastic means it always wants to come back to the original position. Okay, it will apply the same restoration force according to the deforming force that you have applied, right? So what will happen? So it will apply a force in this direction, that is the deforming force. Okay, this is the deforming force. So obviously a restoration force is going to produce. Okay, and suppose the length is been increased up to this much, delta L. Okay, so here you can say in a perfectly elastic body, the strain produced, how much is the strain produced? How much is the strain produced? Delta L upon L, because the original length was L, and delta L upon L is going to give you the strain. Okay, and this strain is always directly proportional to the stress that you have applied. Okay, how much stress you have applied, how much restoration force that you have applied, that much of deforming force. Okay, the deforming force that you have applied, that much of restoring force is obviously going to develop in a perfectly elastic body. Again, the deforming force that you have applied, the same amount of restoring force is obviously going to develop in that perfectly elastic body. Okay, only and only if it is perfectly elastic, right? So I told, what is the formula here? In perfectly elastic, stress is directly proportional to strain. Okay, and if I will calculate this one, then if I will remove, I have to remove this proportionality symbol. Okay, then stress is equal to K into strain. Okay, and this K is equal to stress upon strain. Okay, this constant is known as modulus of elasticity. Okay, this constant K is going to determine, or is going to give us a result, that is what? Modulus of elasticity. Right, and strain will be 1 if the strain is 1. Okay, so what is the formula that we have achieved? We have achieved the formula that is K equal to stress upon strain. We have achieved the formula K equal to stress upon strain, right? So stress upon strain means what? If suppose for an example I have achieved a strain of 1, okay, strain is equal to 1. So what is the formula right now? K equal to stress upon 1. So what is the stress? The stress is equal to K. So here I got the definition of your K. Okay, if I will make strain is equal to 1 for an example. Okay, what is that method? Unitary method. In order to define something, you have to take 1 each, right? So if I will have taken the strain is equal to 1, the K is equal to right now what? Stress. And now here I got the definition of your K. What is K? The K is, you can say, the modulus of elasticity, that is K. Okay, the modulus of elasticity is the stress required to develop a unit strain. Okay, so the modulus of elasticity is what? Is the stress required to develop a unit strain. Unit means 1. Okay, according to the result I have defined it. Okay, so how you can define it? Modulus of elasticity is the stress required to develop a unit strain. Okay, and what the graph you will achieve for a perfectly elastic body? You will get a graph if this x-axis is stress and this is strain. So stress is directly proportional to strain, and you are going to get a straight line. Okay, so this is of 1 mark, this graph. And what is modulus of results elasticity? This is also 1 mark, and Hooke's law carries of 1 mark. Okay, and all the definition carries of 2 marks each. Okay, now let us go through some few definitions of your elasticity. First one is modulus of elasticity, right? That is Young's modulus. Young was the scientist, and he has given also one Young's modulus of elasticity, and that ratio is normal stress to that of the longitudinal strain, and that is working. Young has found out this is only working in case of longitudinal objects or longitudinal activities. Suppose this length is L and you have applied a weight here and it has increased up to a length delta L, right? So then how can you will calculate Young's modulus? This Young's modulus is nothing but the normal stress to that of the longitudinal strain. The formula is, this is already a derived formula, or you can say practical formula. There is no derivation on it. Okay, so Young's modulus is what? Normal stress to that of your longitudinal strain. Okay, so what is normal stress? Stress formula is F upon A, force upon unit area. And what is longitudinal strain? Longitudinal strain is delta L upon L. Okay, Young's modulus, it is a modulus of elasticity is what? Modulus is obviously a ratio, right? So ratio we are going to find out. Okay, so if it is F upon A, this is delta L upon L. So if you will arrange, then this will be F by A multiplied with L by delta L. Okay, so now if F equal to mg, if I will work here F equal to mg, okay, and I will write it here, this will become mg and this is L, so this is mg into L divided by delta L into A, delta L into A. So for a longitudinal concept, for the wire, obviously we have to take the cross sectional area, right? So this is pi r square. Okay, this area is, I have to replace it with pi r square. Okay, so this formula is changed to mgl divided is, instead of A you can write pi r square into delta L. Okay, so this is Young's modulus. So Young's modulus has two formula. One is what? Normal, that is F by A into L by delta L. This is one formula. If suppose only radius is given and area is not given in the question, then you have to go for pi r square, right? Then the formula is changed to mg into L divided by pi r square into delta L. Okay, now moving on to the next one, that is bulk modulus. The bulk modulus is the ratio of normal strain stress up to that of volumetric strain. Okay, it is the ratio of normal stress to that of volumetric strain. Okay, this is what? Bulk modulus. Obviously modulus is what? Any modulus of formula is, modulus of elasticity formula is stress upon strain, because you are going to apply stress and that much of strain is going to be produced, right? That is, strain is what? Change in configuration, right? Change in the structure, right? So that is because of what? How much it has created a stress on it. Okay, and that is depending on what? Deforming force as well as restoring force, because you have applied the deforming force, because of that a restoring force is being created, and stress is depending on what? Restoring force, and the strain is the calculation of change in configuration to that of original configuration. So what is a bulk modulus formula? Normal stress to that of volumetric strain, okay, for a bulky material. So what is a normal stress formula? Force upon area, and volumetric strain is del V upon V. Okay, volumetric strain just now we have found out in the last page, you can check the note, del V upon V. So if I will arrange, this will become F by A, and obviously this V is going to the top, so that's why it will become V upon delta V. Okay, so the formula is F by A multiplied with V by delta V. If it is a sphere, then you are going to apply the formula for V as 4 by 3 pi r square. That's a different structure. Third one is for shearing concept. Okay, this is for what? Volume concept. First one is for what? Longitudinal concept. Okay, first one means this one, Young's modulus, is for longitudinal. Bulk modulus is for volume, and modulus of rigidity is for shearing concept. Shearing concept is what? Suppose you are applying force on the surface making 0 degree with the surface. Okay, if you are applying a force making 0 degree with that of surface, then you can say it is a shearing stress is going to be produced. Okay, now what is the volume modulus of rigidity? The modulus of rigidity is tangential stress to that of the shearing strain, because the stress that you are going to apply, suppose this is the body and this is the thing like this, okay, structure, and you are applying with a rod, okay, this is the rod, okay, and you are applying a force in this direction by making 0 degree, so obviously it is known as a tangential force, and the stress produced is tangential stress. Okay, as it is a modulus calculation, okay, so what you have to do, it is nothing but stress upon strain. So what stress? It is a tangential stress. If you are going to, if a tangential stress is produced, then what kind of strain is going to produce? Obviously shearing. Okay, that concept is known as what? You have to bend this one. The box is like this. Okay, again, suppose, wait, suppose the box is like this. Okay, and you have applied the force in this direction. Now box is being bent like this. Okay, the box is being bent like this. Okay, let me draw again. Previously the box is like this. Okay, after applying the force, the box is being changed. Okay, like this, it will bend like this. So what is this one? This change length, delta x width, and this length is L. Okay, so how you can find out? Okay, how we can find out delta x upon L, that is this theta. This theta is going to give you the result of shearing strain, and this theta is nothing but what? Arc upon radius. So what is arc? Delta x, okay, length L. Okay, so theta equal to delta x upon L. So same formula I am going to apply here. What is that? Tangential stress upon strain. Okay, tangential stress is obviously any stress. Formula is force upon area divided by shearing strain. So what is the shearing strain formula? Theta. Because by looking at to the angle theta, you are going to tell how much it has changed. Okay, and anything that is related to change is dealing with strain. Okay, and for strain, that is what? Theta. So F upon A divided by theta is nothing but this A will go here. This is F by A theta. Okay, and theta, what is the theta? Theta equal to del x upon L, right? Apply the formula here. Instead of theta, it will be del x upon L, and by L is there. So this L will go to top side and will be placed here. Okay, so the formula is F into L by A into del x. Okay, so next time we are going to do some numericals based on this formulas.